Okay, I'm not Fang actually. I'm Jingtao because Fang cannot come. And well, I'm very happy to be here because although I have published several papers for IR, but this is my first time to be here to present in person. So, remarkable time for me. And this work is joint work by Tsinghua University, Renmin University of China, and Xiaohongshu. The other authors are Yan, Qingyao, Jiaxin, Weihang, Jia, and Yiqun. So in 2020, OpenAI proposed the scaling laws for language models, and it is a very significant law that drives the researchers and engineers to keep scaling up the language models. It describes a precise power law relationship between the model performance and several training factors. And the performance is quantified by the perplexity of the next token, and the training factors are the model size and the data size. At the bottom, we can see three figures. This is I copied from the OpenAI paper. You can see that the x-axis are the training factors, and the y-axis is the model performance. You can see that the data points all fall along a straight line, meaning that if we further scale up the training factors, we can expect the model performance will continually be improved. And more importantly, we can know exactly how well they will be improved. So this scaling law is very important for large language model scenario, but we wonder whether this also holds for information retrieval and whether this can bring a maybe large retrieval model area for us. So in this paper, we investigate whether scaling laws also hold for dense retrieval models. And dense retrieval, you have a document encoder and a query encoder. And the document encoder and query encoder embed the documents and queries to embeddings, and you use embedding similarity as a relevant score. In fact, dense retrieval and large language models share many similarities. In architecture, they both use transformer-based models, and in terms of optimization, they both maximize the probability of predicting the target over several candidates. So maybe that dense retrieval will also follow a similar scaling law as those observed in large language models. And in this paper, we try to answer this question in 3 steps. At first, we need to evaluate the model performance with a smooth function so that we can know how well the model actually performs. And in the second step, we investigate how different training factors affect the model performance. And in the third step, we try to answer the question that whether our observed scaling laws imply in practical scenarios. Now first, let's take the first step, that is about how to evaluate the model performance. At first, when we conduct this research, we use traditional error metrics like SIGIR and recall, but soon we realized that it is not appropriate. The problem with this metric is that it only takes input of the ranking list, but it does not consider the output scores. And it means that they are discrete metrics. It cannot precisely distinguish the subtle differences between different ranking models. So to address this problem, we take inspiration from large language models. They use the probability of retrieving the target token as a metric to quantify the model performance. And similarly, we propose contrastive entropy. It takes the input of the probability of retrieving the target passage as the metric. So here is the equation. The softmax is actually the probability, and we use the log form as our metric. At the bottom, we show 3 figures that plot the relationship between our proposed contrastive entropy with 3 error metrics, that is MAP, NECG, and recall. You can see that generally they are positively correlated, linearly correlated, but at the middle, you can see a small break with a little jump on the y-axis. This is actually because the traditional error metrics are discrete. They are not a smooth function. But on the other hand, if we use contrastive entropy, it is smooth, and it can help us to investigate how different factors affect the model performance. So now we will use contrastive entropy to evaluate models, and we can now investigate the scaling laws for different training factors. The first training factor is the model size. You can see there are 2 figures. On the left figure is the experimental results on an English dataset, that is MS Marco. And on the right side, it is experimental results on a Chinese dataset. And the x-axis is the number of parameters, and the y-axis is the contrastive entropy. There are many data points because we train many checkpoints, and we try to investigate how how scaling up models affect the model performance. And you see that the data points almost fall along a straight line, meaning that if we further scale up the model size, we can expect the contrastive entropy to be further improved, and we will know how exactly they will be improved. The equation for this line is here. You can see, wait a minute. It's here. On the left side is contrastive entropy. On the right side, there are two terms. In the first term, n means the number of parameters, and a and alpha are coefficients. It means that if we increase the number of parameters, the contrast entropy will decrease at the log rate. The second term is a irreducible term. It means that even if we use a very large model, we cannot decrease the contrast entropy to 0. It is very reasonable because even human annotators cannot agree with each other sometimes on whether a passage is relevant. So we cannot expect a model to perfectly align with our human annotations. And this is a model scaling law. The second is a data scaling law. Similarly, we conduct experiments on English dataset and a Chinese dataset. The x-axis is a number of annotations, and the y-axis is a contrastive entropy. We have several data points, and they all fall along a straight line. And this line also tells us that if we keep scaling up the number of annotations, we can expect the contrast entropy to be further improved, and we know how exactly they will be improved. This is the equation. Similarly, we have two terms. D is the number of annotations, and this shows that if we increase the annotations, the contrast entropy will be improved by a log rate. The second is also a irreducible term. Now we have the two scaling laws that shows how scaling up the model size or data size affects the model performance. We wonder whether we can have a joint law that we can know how the model will perform given different combinations of the data size and the model size. Can we do that? Yes, the answer is yes. And the figure shows the different data points. Different color corresponds to different number of parameters. And the x-axis is the number of annotations. And the dotted line is a fitted curve with using this equation. The first is also a exponential decay term, and the second term is also a irreducible term. This means that we can exactly predict how well the model performs given different combinations of training factors. So this will be a powerful tool for us in the future to use when we try to decide how much data we will annotate and how large a model we want to train. So let's give a brief summary. We have talked about how we can evaluate the model performance with contrastive entropy, and we give three scaling laws. The first two are the model scaling law and data scaling law, and the third is a joint scaling law that can enable us to know how well a model will perform given different combination of model and model size and data size. So with these tools, we want to answer a very big question. That is how this means in the future. Should we really scale up the retrieval model? This is actually a very big question, and we do not have a direct answer, but we want to give some hints in three perspectives. The first is a budget allocation scenario. The second is about the irreducible term in our equation. And third is how well this improvement in contrast entropy results in other metrics that is closely related to user satisfaction. In the first situation, it's about the budget allocation. We assume this is a scenario that you have a limited budget, and you can either use this money to scale up the data annotation so you have more training labels, or you can also choose to train a very large model. But the downside is that you need to spend more money on the training and inference. So this may be a tough decision, but luckily we have the joint scaling law that tells us how different combinations of data size and model size will result in the model performance. And we can use the joint scaling law to help us decide in this scenario. So there will be two situations. In the first situation, we do not consider the inference cost, which means that you will use all your money on the data annotation and model training. So in this situation, if you have $20,000, the optimal model size is 10 billion. So yes, in this situation, you should scale up your model, and you should not use the BERT-based or BERT-large model. You should use something like Llama. In the second situation, we consider the inference cost, which means that you need to use your budget to index all the web pages, and you need to deal with many user requests. And in this scenario, even if you have $20 million, the optimal model size is just 40 million, which is even smaller than a BERT-based model. So you can see that for us, information retrieval researchers, we should really consider the inference cost because we really have many, many web pages and we have many user requests. And as for whether we should scale up the model, we should really consider whether we can afford the inference cost. So this is the first perspective. And the second perspective is an irreducible term. Actually, in our study, we find this term is substantial. It really means that even humans cannot agree with each other as to whether a passage is relevant. So we can't expect a model to perfectly align with the human annotations. So I see we have experiments on the English dataset and a Chinese dataset. On the English dataset, our largest model can reduce the contrast entropy to 0.05, and the irreducible term is 0.04, which means that even if we scale up the model size and data size, the maximum gain is just 20%. However, on the Chinese dataset, our largest model can reduce the contrastive entropy to 0.5, and the irreducible term is 0.14, which means that on this dataset, you can potentially get 7% gain on the contrastive entropy. So we mean that you should really focus on the irreducible term because this means the upper limit of the benefits of scaling. So this term can tell us a lot, and it really varies in different scenarios in terms of how this dataset is labeled or how these relevant signals are actually defined. So this is the second perspective. The third perspective is how well this improvement in contrastive entropy results in other metrics that is closely related to user satisfaction. In our previous slide, we showed that the SIGIR or other traditional error metrics is almost linearly correlated with contrastive entropy, so the gain is almost linear. But if we contrast these results to other results from large language model studies, in large language models, some find that this improvement in a similar contrast entropy loss term can result in something superlinear, like emergent phenomena. And so this is very different. So in that scenario, maybe scaling up has more benefits. And we believe the potential reason is that the two models are used in very different ways. In this study, we use ad hoc retrieval scenario, which means that we only retrieve the passage once. But in large language model, if you want to generate a long sequence, you need to use forward passes many times. So you can imagine that in that scenario, if you increase the success rate of one forward pass by a little bit, it can bring a large gain when you generate a long sequence. So this is a very different scenario, and we believe that maybe in a situation where you need to retrieve passage more than once, something like multi-hop retrieval, that can further improve, that scaling can bring more than just ad hoc retrieval. So this is the third perspective on the metric improvement. And let me conclude this presentation. We talk about how we should quantify the model performance with contrastive perplexity. And we also discuss how model size and data size influence the model performance. And finally, we show our thoughts on how these imply in practical scenarios. We believe there is much to do in the future. We should further scale up model size and data size, and we should explore how different training strategies and model architectures influence the scaling laws. And finally, we believe that scaling may have different benefits in different scenarios, and we should explore how this work out in different scenarios. And that's all. Thank you.